So as the remainder of people hopefully quickly get checked in, since we have a class that's going to follow this lecture, I want to make sure that our distinguished lecturer has opportunity to tell us all about all the great things she's been working on. And so I'd like to get things underway. So please, if you can, quietly check in and take a seat so you don't interrupt other people's paying attention to the seminar today. It's my pleasure to invite and to serve as a host for my colleague, Professor Lan Yang, the Edwin H. and Florence G. Skinner Professor in the Department of Electrical Systems Engineering at Washington University in St. Louis. Professor Yang earned her bachelor's degree from University of Science and Technology of China, and she earned her PhD in applied physics from Caltech in 2005. Professor Yang received the NSF Career Award in 2010 for her work on single nanoparticle detection and sizing using on-chip optical resonators, and we'll hear some things about that today. She also was honored with the 2010 Presidential Early Career Award for Scientists and Engineers, known as the PCASE Award. That's awarded by the President of the United States. She's published many things in fantastic journals, including Science, Nature, and Physical Review Letters, and she is a fellow of the Optical Society of America. So I'm pleased to welcome Professor Yang. We have a small gift from the ECE department to recognize you and thank you for coming here to give our Granger Distinguished Lecture. The big orange box is a plaque to commemorate the occasion. I don't know what's in the smaller orange, or the smaller orange and blue box, but of course it's very Illini.
Thanks a lot.
So, and welcome, and thanks so much for taking the time to visit us and share your work with us today.
Thanks a lot. This is really my great honor to be here. I was here 10 years ago when I just started my position at WashU. And so when I say UIUC is special to me, I'm not exaggerating because, I'm a super fan of great researcher and great researcher with great character. I have known people like Professor Gary Eden for 15 years, and I know Professor Brian Cunningham, and also Gaurav is more like a member of my academic family. A lot of great people here, and this afternoon I happen to have a chance to meet with my former undergraduate students working in my lab. She told me how grateful she feels at in this school. So all echo is what I feel about the UIUC. That being said, it is really my great honor to be here to share my research with all you guys. And I also wanted to actually told Brian just now, I just came back from China 2 days ago. I was supposed to have jet lag. However, starting from the morning meeting with Gaurav, I feel excited all the way because all the people, the faculty member I've talked to are just great researchers. They give me the brilliant idea and it's exciting things to share with me. That really makes me feel like, you know what, this is a great family and it's wonderful all of you have a chance to be here. And it's an honor for me to share my research. As you can see from the title, today I'm going to explain what is Reciprocal gallery microcavities and their applications. And for me, actually I have 60 slides, and it's mission impossible to give you all the details within 45 minutes. So I will just skip some of the slides. I will leave, and Brian emphasized I should save 50 minutes for students. So feel free to ask me questions if I skip too much details. So let's start from the first slides. When we do research, we want it to the motivation, right? Only when you have strong motivation, you are passionate about the things you're working on. For me, in general field of photonics, I think what is the most important thing is about photonic structure. It's about light-matter interactions, right? If you wanted to make use of light, you want to enhance light-matter interactions. And for all the many kinds of optical devices, optical resonator is such a device. Within certain physical volume, light is confined, and that confinement significantly enhances light-matter interactions. Let me give you one simple example showing the traditional design of an optical resonator. Think about the two mirrors, face aligned very well, and then if you find a way to couple light in such a structure, then the light field will be bounced back and forth by the mirror, right, and circulate around, right? If there is anything inside the resonator interacting with light field, you can see, depending on the number of round trip that can be finished by the light field, that will decide light-matter interactions. Then what is parameters tell you the number of round trip that can be finished by the light field? As that being said, it should be related to the decay time, right, the lifetime of the photon in the cavity, right? So here is a slide telling you what is a figure merit, a quality factor that we use to characterize the quality of an optical resonator. It's defined as stored energy over energy loss per cycle. So think about extreme case. If you have an ideal resonator, there's no loss at all. The denominator will go down to 0. So Q will go to infinity, right? So the higher Q, the lower the loss, so they're related. And as you can see from the equation, you can see the Q factor is related to the decay time, right? This is a time domain behavior, and this is the experimental data we collected in the experiments. So you can see the exponential decay. From the decay time, you can get the quality factor, right? And if you happen to know a little bit about Fourier transform, you can see that if you apply Fourier transform to this equation, you have another new equation. This equation should tell you the spectrum, what the spectrum looks like in frequency domain. So here, this shows a Lorentzian line shape function. And here, I show this spectrum in frequency domain. And that if you look at this formula, you can see the line width of this line shape is related to the quality factor. If you do a little bit more math, then you're going to find out the quality factor actually is related to this ratio. Resonant frequency over the line width of the mode you can observe in the experiments. This is a routine process we do in the lab to characterize the quality factor of a resonator. And okay, so there are many kinds of ways to confine the light, right? This, as I said, this is a traditional design, have some reflecting surface that can confine light within such a volume. But if you think about the shrink such a design to microscale is very challenging. First of all, you need to think about polish a very nice mirror with very high reflection coefficient, so light is bounced back and forth. For such a microscale mirror, you need to line them very nicely. So light will be, bounced back and forth, right? And that being said, it's a lot of challenge and difficult to make this in microscale. So here comes a strong interest in another kind of resonance structure. Initially, this has a different name. Now we call whispering gallery mode resonator. It also has another name. It's called morphology-dependent resonator. That being said, this resonance effect is affected by the morphology of the structure. So such a structure has some very nice feature we wanted to have. For example, it can be easily made in microscale, and you can achieve high quality very easily. And the fabrication process is straightforward. And why such resonator have such a name, whispering gallery? So think about this cathedral dome. This structure is called whispering gallery structure. In such a structure, a single whisper can be heard throughout the gallery spaces. So you can see this effect is called whispering gallery, right? And this, as I noted here, in early 20th century, Lord Rayleigh already found this effect for acoustic wave. But acoustic wave is just a kind of wave. How about shift this spectral domain to light wave? Yes, it did work very well. And before I show you how it works in the optic domain, here are all the structures. You can see that that will have such effect. For those of students coming from China, next time when you go to Beijing, go there. You will see the effect. This building have a Chinese name. It's Huiyinbi. That actually indicated such effect, whispering gallery effect. Okay, so let's see how it works in the optic domain. So if you form a structure with circular boundaries, such as microsphere, microdisc, microring, all kinds of structure have a circular boundary. And if you find a way to couple light in such a structure, similar to those counterparts of acoustic wave, light wave will circulate around just along the boundary, right? This is what we call the optical whispering gallery mode. and it works very well. And here is a slide showing why we care about ultra-high Q microscale structure. This is a simple formula showing the power buildup factor. Tells you, for example, the B power buildup factor is defined as ratio of circulating power in the cavity over the input power. And you can see the power buildup factor is proportional to the Q factor and the inverse of diameter. So the higher the Q, smaller the cavity, the higher the buildup factor, right? Let's put some numbers into this formula. Those numbers can be achieved easily in the lab. Say, for example, a Q factor of 10 to 8, a microscale resonator, you put the number in the formula with the input power of just 1 milliwatt. So what is 1 milliwatt? The power coming out from the laser pointer is a milliwatt. It does, it cannot do much, right? But if you couple light in such a resonant structure, it will enhance the circulating power greatly. Say, for example, the circulating power will be 100 watt. And think about the lifetime, that is 100 nanosecond. It is short compared to the lifespan of human being. But think about the propagation speed of light, that is 3 times 10 to 8, right? Meter per second. So that being said, this photon, or the lifetime is just 100 nanosecond, but it can propagate for 30 meters. If the round trip of the resonator is in microscale, then the round trip that can be finished with the light field could be up to 1 million times. Such effect can dramatically enhance light-matter interactions. So there are many applications that it has been chased after by researchers all around the world. Because of limited time, I wouldn't be able to cover all of them. So for example, for those of you who are very interested in optomechanics, this is linked to such effect, radiation pressure in the resonator can trigger some mechanical oscillation. A lot of things can be done along this line of research, such as non-reciprocal wave transport and sensing. For those of you who are interested in this topic, actually you have faculty member here, Professor Gaurav Bal. He is in mechanical engineering department. He is an expert for this line of research. And for me, I focus on these 3 topics that is focused on my lab. That is sensing, period-time symmetry, and non-emission physics, to see how they are pursued in such a tiny device. So for sensing, as you can see, if you have Reciprocal gallery structure, wave is just propagating on the boundary. So anything attaching on the surface will make the changes, will disturb the light field, right? Which will be reflected as changes in the transmission spectrum. Here, the transmission spectrum we have, this makes sense because think about for some light that is on resonance with the structure, it will be confined inside, so it doesn't leak out. If you look at the transmission spectrum, those lights will show up as resonance deep because the energy is stored here, right? So that is a normal traditional spectrum. And if anything attached on surface disturb the light field, the changes will be reflected as either resonance shift or line width broadening. So it's really sensitive. A lot of research all around the world are chasing after this direction and has demonstrated many kinds of sensing applications, such as detection of molecule, DNA, protein, or dynamic or protein-protein binding. It's a very active field in our community. And here I want to explain a different sensing modality that is self-referenced sensing mechanism. So still start from this single resonance, we notice that actually this effect that is linked to light scatter in the resonator. If there is light scattering within such a structure, the single resonance will split into 2, and by some quantitative analysis, you can trace back the features such as size, refract index of the light scatterer. So I will explain how it works. Before I show that, I will just show what has been done before. Thanks for those pioneering researchers such as Frank Vollmer, Steve Arnold, who has this pioneering research in our community, who has successfully demonstrated back, I think, 15 years ago, that a whispering gallery resonator can be an ultra-sensitive biosensor. It's based on this single resonance shift. And here we have found actually doing Okay, but here I want to emphasize the importance of literature search. So here actually you can see the year this paper was published, right? Like tens of years ago. People already found that in a waveform gallery structure, if there is defects or nanoparticle on the surface, a single resonance can split it into two. So we're definitely not the first one to find out this phenomena. But here we ask different question. So the same phenomena, but different question, that is, okay, you see this phenomena, can we make very good use of this mode splitting and trace back something valuable? Okay, it's like, you know, everybody have a dream, right? But it's possible that a dream can come to be true. You know, it's very lucky in all cases we succeed. And it turns out it works very well. Those are the two graduate students who really made this work. Here is the illustration showing how it works. Think about a waveguide coupled with waveform gallery structure. If light is coupled from left to right, you can see the clockwise mode is excited, right? But just clockwise. And think about this is circular symmetry. There actually does exist another mode. It just doesn't, it's not just excited. So there should be another mode that has a spectral degeneracy with this clockwise mode. That is mode in the counterclockwise direction. But there is no energy coupled inside until there is a light scatterer that helps to couple some of the light into the opposite direction. And because of this coupling, those coupling lift the degeneracy of the two modes. And then initially you can see you only have one mode because of this coupling which lift the degeneracy, then two modes shows up. And this two modes is initiated by this nanoscatterer. And thanks for another research, this paper published in the Physics Review Letter in 2007. It shows theoretic models. You can see it link those spectral features with the properties of this light scatterer. See here, for example, 2G is separation of these two modes that can be measured directly, right? And what is big gamma? The gamma is line width difference of the modes that can be measured also directly. And what about the alpha? Alpha is polarizability of the scatterer. For a spherical particle, you can write down the formula explicitly. The polarizability is proportional to the size. Okay. What is F? F shows the overlap of this light field with the nanoparticle. And omega is resonant frequency, you know that, and V is mode volume. So for first conference paper, we just run some simulation, have some guess about the numbers, and show that mode splitting can be used for sensing. But a couple months later, you know what? Now it looks straightforward, but when we first found it out, we didn't notice. If you take a closer look of this formula, now if you look at it individually, it's not a convenient sensing mechanism because it's position dependent, right? You need to know what is F. That's not a user-friendly measurement. However, if you take a closer look and get the ratio of the two parameters, those challenging parameters are gone. Then gamma and G, the ratio is only related to the polarizability. It's a very neat measurement. So we design experiments and we deposit particle one by one on our resonator. You can see this intensity graph shows how the spectrum changes with time when you introduce particle one by one using such a simple formula, and it works out. It turns out with such one further step of this process of this formula, we achieve this position independent measurement because it's nothing to do with F function, right, which shows overlap of the particle with field. It's position independent. In a single shot measurement, you got the size information. And this just shows some optical micrograph, shows that if you have a clean resonator, you have a single resonance. When you introduce particle one by one on the resonator, you can see gradual discrete changes in the mode splitting spectrum, right? And from those quantitative measurement of mode splitting spectrum, we can trace back the size of this nanoparticle down to 15 nanometer. Here I show the movie that initially you have a single resonance, then we gradually introduce a nanoparticle one by one. You can see the changes, separate changes, right? Mode splitting. And to convince others not in our field to say, you know what, this works. We do need to have control experiments to compare our method with the standard method. So here we compare the size measured by whispering gallery sensor with those data collected by scanning electron microscope, SEM. And the data shows pretty well. You can see the data matches pretty well, right? So by then, we're confident. We did demonstrate a new sensing mechanism, a new sensing technique. It can be used to achieve not only detection, but quantitative measurement. And you don't need a special control of the device. You don't need a high temperature or vacuum control. It's just, it can be operated just in air. So it can be found for a lot of applications, such as environmental monitoring, to see the particle flowing in the air, to get distribution of those particles. So here is fun experiments we did. Say, for example, this is blind experiments. The students can mix different particles. It can be the particle with similar size, but different chemical composition, right? It's a virus when the gold, you can clearly see different distribution, or you can the particle could be the mixture of the same particle but different size. You can still see, now we can clearly differentiate different kind of particles. So that being said, this is, I think is a novel method that can do things complementary to other kind of sensitive sensor for nanoscale structures. And I need to speed up, so forgive me for not being able to give you too much details. We can always discuss after my talk. And I wanted to also emphasize the contribution from others. So in addition to what I've done, right, most splitting and many others are trying to enhance sensitivity. For example, there is this panel shows integration of plasmonic effect with this resonant effect, which helps to further boost the sensitivity of this whispering gallery sensor. And here's another work to use whispering gallery for imaging. This is very smart, neat experiments done by Randy Goldsmith group in University of Wisconsin. So what he did is probe and pump experiments. So here there's fiber, right, that used to couple light inside, and they monitor the transmission spectrum. And there's a pump from the top. The pump scan on top of the resonator. Whenever the pump hit the, it overlaps hit this nanostructure. If this nanostructure was heated up, that effect will shift the resonant frequency. So basically, by monitoring the transmission spectrum, they know where the particle is. By doing that, they can do the thermal mapping. It's a beautiful work for just imaging. And also another work I really like is from Bau's group. He uses optomechanic effects. Say, couple light into the structure because it's power enhancement, right? It's strong enough to excite the mechanical movement, mechanical modes. What he did is to monitor the changes in the mechanical modes and trace back the information of the particle flowing through this pipe. The uniqueness of his sensing technique is whispering gallery mode is just on the boundary, right? We can only detect things on the boundary. For his idea, the acoustic wave cover all the cross-section of those channels. So for anything flowing through the channel will be captured. So there are a lot of interesting medical applications. And also, I want to emphasize, before finishing the part about sensing, that the whispering gallery is the application for whispering gallery sensor is not limited to particle and molecule sensing. It can also be used for wave sensing. As I said, anything that can perturb or disturb the light field can be captured by the transmission spectrum, and we can trace back what happens there. Say, for example, my student did such experiments. We tried to do acoustic sensing. What happened is, if the acoustic wave passed through the whispering gallery structure, it's like a pressure wave, changes the refractive index, right? That kind of changes is reflected as resonance shift. So by monitoring that, we can characterize quantitatively the acoustic wave passing through the structure. And here is the photoacoustic imaging we collected using our whispering gallery sensor. This image is compared with the images collected by the commercial acoustic transducer, and you can see the results is pretty very encouraging. Okay, so much. I already used half of my time. I will switch my gear to another interest in my group that is more related to physics, parity time symmetry, and non-Hermitian physics. I will show 4 case studies. The title looks very different, but I want to show you they are coherent, although visually they look different. The first one is about Pd symmetry and use effect to achieve non-reciprocal light transmission, something like optical diodes, right? And second one is loss-induced revival and suppression of lasing. This is kind of like a counterintuitive. How could you use loss to revive laser? I will explain. Actually, we didn't break any fundamental rule, but we did play some trick there. And also the third one is about, here when we work on this project, we found so much fun with exception points. That's something we found in the second project. Because it's so much fun in this project, it led to the third one. So we decided to zoom in and take a closer look at exception points and found actually these exception points can be used to achieve chirality, that can be used to achieve direction lasing. And still not enough for my students. So we designed another experiment around exception points. That is, there are some interesting topological features around exception points that can be used for enhanced sensing. So we draw a circle, right? I start from sensing. Now move along the line for Pd symmetry and exception points, then back to sensing. So those scattered dots are all connected. Hard work is never wasted. And okay, so what is motivation to work on Pd symmetry? Those are the most, I think, fascinating subjects in photonics, right? Photonic crystal, metamaterials. And tell me why people are so interested in this field or this topic. My interpretation is those are not just a simple device. They give people some idea about a design idea. So different research group, different researcher, they can follow specific rules and make their own design. Everyone can make their unique contribution. So that being said, yes, work on specific devices, of course, is very exciting. But what makes me feel more exciting is if we can find a way to develop a new design route that can allow us to fabricate some artificial structures with properties unattainable in naturally existing materials or systems. So Pd symmetry, here it comes. So these are the structures. You can see different colors are used, right? Those colors are used to label some specific features that will be explained in the next few slides. It's like playing Lego, right? Like my daughters are super fan of Lego because although the building blocks look similar, but depending on how you design that, you can make those building blocks into a house or into both, depending on the design, right? See if we can provide a new mechanism. Here, as I put the notes here, how can we use Pd symmetry as a design to create some new design method? So before I show you how it works, let me explain what is Pd symmetry. So for those, it started from this, I think, in quantum mechanism background. Say if you want to study a closed system, an ideal system, a system without energy exchange with surrounding medium, mathematically, theoretician, they will use this Hermitian Hamiltonian to do the math. When they do the math, then they calculate the eigenvalue, right? Just math. Do the eigenvalue, they can find, for those closed systems characterized by Hermitian Hamiltonian, the eigenvalue is real. However, if you want them to study an open system that the energy exchange with surrounding medium, then you cannot say it's Hermitian Hamiltonian. It's non-Hermitian physical system. If you solve the math, it will tell you the eigenvalue is complex. Okay, so is there something between an open system but have real eigenvalue? In 1998, Carl Bender proposed this. Yes, such a system does exist. There is such a Hamiltonian. It's non-Hermitian. However, if you solve the math, it will give you real eigenvalue. And I will use my system to explain how it works. And so he pointed out to have such a Pd symmetric system. It's an open system, but if you have a subsystem within which laws can be balanced by the gain, then it is Pd symmetric. If it's Pd symmetric, then it has real eigenvalue, even if it's an open system. Okay, for those of you who love math and physics, please refer to his first paper, published in Physics Review Letter in 1998. So let me give you, I prepare a few slides, give you this brief picture of how it works. So Schrodinger equation is kind of very useful tool, allow you to understand how a physical system evolves with time, right? So we use this Schrodinger equation to describe your system. And we say, you know what, how about we apply, we use this to study Pd symmetric system, right? If you apply the T operator, time transformation to this equation, what you need to do is change the sign. T becomes minus T, right? T transformation. And then you apply the P transformation. P is more like a spatial transformation. Spatial, think about the spatial variable. So under the P operator P transformation, the X, the spatial variable, change the sign, minus X, right? You combine them together, Pd symmetry, you have a new equation, right? This one. And if you say, I want my system to be Pd symmetric, that means if you want a psi to represent the solution of your system, then you apply Pd transform on this solution. You have a new one. You want this to be also solution of this Schrodinger equation, right? Because you want this system to be Pd symmetric. And then you compare this two equations, these terms one by one, then you can reach a conclusion that is the potential function should satisfy this condition, potential function. So if you break this potential function into real and imaginary parts, here is what we have. You want the potential function, the real part of the potential function to be an even function, the imaginary parts of a potential function to be odd function. So here I want to bring out another important papers. This was published by Chris Delitis with his colleague. They deciphered this physics and pointed out this in an optic system, the potential characterizing an optic system is linked to what? The profile of refractive index. So that being said, if the potential of optic system is related to the refractive index profile, then they should have similar relationship as I have shown here, right? So again, let's break it down, the refractive index into two parts, real and imaginary parts. Okay, so now you see the interesting things about Pd symmetry. Pd symmetry forces us to think about the imaginary parts of the refractive index. Normally when we talk about refractive index of materials, right, say like a silica, we always say, oh, refractive index 1.46. That refers to the real parts. Normally we ignore the imaginary parts which linked to loss. But here you don't want to ignore that because this is really critical for you to understand how to form a Pd symmetrical structure. You know, this is, so here you wanted to have this refractive index profile that the imaginary parts is odd function. What does that mean? Here I prepare a slide, explain how it works. Think about this. Think about a plane wave propagating along z direction. This, everybody knows this, right? E to the ikz, characterizing a wave propagating along z direction. And keep in mind, if a wave propagates along a materials median, k is affected by refractive index. So we should rewrite this. If the wave propagating along in the materials median should be e to the I n kz, right? K is this vacuum wave number. Now you see the n refractive index here. If you replace the refractive index here by this form, you see something interesting. Plug this into this formula. Now you see the physical meaning of the sign in front of the imaginary part of the refractive index. Depending on the sign of the imaginary part of the refractive index, it tells you that whether the light field increase or decrease when it propagates along z direction. If you say I want a physical system that has refractive index profile shows this relationship, that means in one part, if the refractive index is positive, then in other parts it should be negative, right? And think about the sign. The sign tells you whether light increase or decrease. So that being said, to have a Pd symmetrical structure, you should have subcomponents. Some have loss, some have gain, because only when you have gain, light will increase, right? And for those of you who still wanted to more intuitive interpretation, there's another slide prepared for you. Actually, this is original prepared for news. Now you can see a straightforward, intuitive way to understand how it works. Think about the two components. Under the parity transformation, parity reflect transformation is more like a spatial transformation, right? You just change the position, switch the position, right? And then still such a system, two subcomponents, but now we want to say that one has loss, one has gain. What is meaning of gain? Gain means as time goes by, more energy comes to the system. If you reverse time, what does it mean? The system lose energy, right? So under the time reversal transformation, loss become gain, gain become loss, right? And then you combine them together. If you have two subcomponents, if you initially apply P transformation, switch the spatial position, under the T transformation, then loss become gain, gain become loss. Get back to its original states. So that being said, for a Pd symmetric system, you do have this subcomponent. Some have loss, some have gain, and loss is balanced by the gain. And here we come. The way to build the Pd symmetric structure. And those are the work that have been done. Say, for example, if you have two coupled waveguides, one have loss, one have gain. If you have two passive resonators, what happens is if you introduce loss to the structure, then you gradually decrease transmission, right? Because loss dissipation. However, if you have this PT pair, PT waveguide, if you operate the whole system in this broken phase, then what happens is if once loss past certain value, actually further increase the loss will revive, further increase the transmission. That is kind of counterintuition, right? And here's another piece of very classic work along the line for PT symmetric photonics. So again, this is a two coupled waveguide, PT symmetric pair. And if you operate the system in PT broken phase, what happens is it doesn't matter which waveguide you use as input. The output light always come out from the waveguide with gain median. So it's not reciprocal. So this are two work that has been done before. As an expert in the field of resonator, so we want to apply the concept to the coupled resonators. So what we did is to couple two resonators together, and one of them is doped with gain, and those gain median can be added easily by using some wet chemical synthesis. And the Bopon is the hero of the group, implementing all the experiments, and he made a structure, and it's not easy because you wanted to control the coupling between the two on-chip resonator, right? So you need to make this resonator fabricated on the edge of the chip. This I think more than half a year for him to figure out the fabrication. So here, just a simple slide showing you what chemical synthesis we use to introduce gain median inside. This is a video I recorded. You can see that the Wishbone gallery mode is really on the boundary, right? Okay, now we have the resin with gain median. We couple them together, and here comes this data we connected from this resin pairs. And we also show the control experiments. So the red line shows the results coming from this traditional pair, the passive coupled resonator. And the blue curve shows data collected from the PT pairs. So now I have a chance to explain what is eigenvalue in the resonator. So eigenvalue of our resonator system actually is resonant frequency. Okay, and how to understand the real and the imaginary parts of eigenvalue? Think about e to the I omega t. If you break down the omega into real and imaginary parts, what does it mean? The real part of omega still give you the resonant frequency, right? However, imaginary parts is different. E to the I omega t. That tells you, depending on the sign of the omega imaginary parts of omega, it tells you whether the field will increase or decrease as time goes by, right? So that being said, in all experiments, it's straightforward to quantitatively measure the real and imaginary parts of the physical system. The real part is just resonant frequency. The imaginary part is related to the loss, right? As I said in the very beginning, I said that the photon, the loss of the experience by the photon is related to the line width, related to the quality factor. We just need to characterize the line width of the mode. We can get information for the imaginary parts of the eigenvalue. That's how we do the experiments. And the coupling strength is tuned by changing the gap between these two resonators. And you can see when the coupling strength is big, the behavior is similar, right? So let's take a look at this special regime indicated by the yellow color. And in this area, you can see that actually the two supermodes. Why? Because if you look at, although the real part is the same, right? But if you look at imaginary parts, actually they are the two modes. That's a little bit strange because if you look at a conventional resonator, two supermodes are formed. The real parts are different, means the supermodes have different frequency. But the imaginary parts are always constant, are always the same, right? It makes sense because if you look at this coupling between the resonator, think about number 8. That is trajectory taken by the supermodes. It does make sense. These two supermodes experience loss in both resonator. How come those two supermodes have different imaginary parts indicating different loss, right? Because if you think about number 8, it just doesn't make sense. So that puzzles us. We did a few more tests. So think about a black box within which there's a PD pair. If you look at the output and input relationship, you'll find out there is very low power. There is nonlinearity showing up. For conventional coupled resonator, it's a linear relationship. So the nonlinearity could come from many effects in the resonator. You know, this gain saturation, thermal nonlinearity, current nonlinearity. Without looking at the details, there's one paper that is very enlightening. That is this paper by Xianghui Fan. He pointed out, actually, nonlinearity in a physical system is very helpful. It allows us to achieve this non-reciprocal wave transport. So we ask ourselves, can we design experiments to show this non-reciprocal behavior? So here's the experiments we've done. Think about, again, the black box within which there is a Pd pair, Pd symmetrical pair, right? And we define the forward and backward direction. And we notice that if you operate a system in this Pd symmetrical regime, you know, it's reciprocal light transmission, right? If you operate a system in this yellow zone, that is what we call the Pd broken regime. But if it's operating in linear regime, still reciprocal. However, if we operate the system under the Pd broken phase and nonlinear regime, what you will see is very nice nonlinearity. In one direction, there's nothing. In the backward direction, there's enhanced light signal. Okay, so my students ran some simulation and found this, field localization. Field localization happens here. And field localization helps to enhance the nonlinearity. And now now looking back at the data, now it makes sense. Look at this Pd pair, right? This is what we call the Pd broken phase. You have two supermodes. The frequency, real parts are the same, right? But imaginary parts are different. How? Because field localization. One of the supermodes is localized here, another mode is localized there. So field localization nicely explains why the supermodes have different laws. So that's of our discovery in this project, right? And to summarize, so using this Pd pair, field localization, we dramatically enhance nonlinearity to achieve this non-reciprocal wave transport. Based on this project, we asked ourselves, can we expand this concept to a broad setting, such as non-Pd symmetric system, but with, for example, coupled resonator with different loss. You know, it's just because the resonator with lower loss is more like a resonator with a little bit gain, in contrast to the resonator with a higher loss, right? So we designed the experiment in such a way, coupled resonator, and for this one, we introduced a chromium tip to the resonator. And the chromium tip gradually introduced loss to the second one. Here, again, the experiments are all done by Bo, my graduate students. He did a simulation, found out for such a system, if you gradually change the loss, right? You can see you have two supermodes indicated by blue and red curve. Initially, you can see the two supermodes have different real parts, but but the imaginary parts are the same. It doesn't make sense. Think about number 8. Those are the trajectory taken by the light field, right? However, if you further increase loss, you push the system to such a special points. It's called exception points, at which both the real and the imaginary parts of the eigenvalue coalesce. Okay, and if you increase the loss further, you will see that 2 different supermodes are formed. Now the real parts, now the real part is the same, but the imaginary parts are different. The 2 supermodes have different loss, right? And it definitely shows, because we already know field localization from the Pd symmetry work, right? So we know it is field localization. And we design such experiments. Now we started with a resonator with Raman again, with Raman lasing. And then we approach this resonator with another resonator. We introduce extra loss. The Raman lasing is gone. But then if we further increase the loss experienced by the other resonator, you can see further increase of loss revive the laser. So I would say exception point is a turning point. Once you approach the exception point, you initiate a new mechanism, that is a field localization. So without physically changing the position of the 2 resonators, by just tuning the loss in the structure, the light field will automatically redistribute the light field. Don't you think it's a new mechanism to control photonic system? Okay, time is up. I need to speed up. So those that, as I said, we're not alone. There are many other people working along the same line of research, and you can refer to this literature. And again, as I said, doing research is fun. It turns out that back in 7 years ago, when I was just starting my career, we already found actually when we do sensing experiments, my student found if you use 2 nanoscatter, we can tune the system around exception points. If you take a closer look of the spectrum we have got, this is my first graduate students who did sensing experiments. He shows, you can see by manipulating these 2 nanoscatter, we can get a different spectrum, right? At that time, we know nothing about exception points, but we know this is exception points. We just pointed out just one line, didn't do anything else. But this spectrum shows, those modes collapse at one point. And then 7 years later, my students, again, Bo, said, let's revive what we've done before. Exception points, now without a coupled resonator. Just use 2 scatterer. We tune the system around exception points. So what we've done, we found that at exception points, we can achieve chiral modes. Say, because, as I said, exception point is a spectral singularity that only one state and only one state survive. So now, say for example, if the system is operated far away from exception points, then naturally there are 2 states that can exist, right? Clockwise or counterclockwise. But now if you push the system around exception points, only one state can survive, either clockwise or counterclockwise. So depending on which exception point you choose for your system, we show that the lasing can propagate either in clockwise or counterclockwise, but not both. Only one direction is preferred. So this is for application for chiral modes and direction lasing. So one more project that is about, again, exception points. So 2014, 3 years ago, a theoretician pointed out that if the system is operated around exception points, actually you can enhance the sensing performance. So why is that? If you look at this exception point sensor, right, at this position, the mode is degenerate because only one mode can survive, right? Only one frequency on one state. So what is the difference of this with this traditional design? This work was done by my graduate student Wei Jian. So he designed experiments. Here's what we found. For this traditional design, as I said, as I showed as the first project, right? Naturally, for a clean resonator, you have you can see there's only one resonance. There is a kind of spectral degeneracy, but this degeneracy only applies for frequency. There are 2 states. The mode can propagate in either clockwise or counterclockwise. Whenever there's a particle come in, it will excite the other states, right? So 2 states does exist. However, for exception points, there is strong preference to only one state, depending on which exception points you choose for the system. So it's kind of different degeneracy. And if you look at it as energy splitting with respect to the perturbation, the reason this is called diabolic points is because if you look at this figure, it's very much similar to this Chinese yo-yo. It's called a diabolo. This is diabolo structure. So that's why this degeneracy is called diabolic points. If you compare the sensing performance, the starting point is the same, single resonance. However, the results are different. For the sensor operated around exception points, the mode splitting is larger than what is observed in the traditional sensor. If you take a closer look at how those topological features showing how the energy splitting changes with respect to the perturbation applied to the modes, you can see conventional sensor, there's a linear relationship. For the exception point sensor, there is a square root relationship. So if you think about a very small perturbation, if you think, for example, a small number, right, 10 to minus 4. For the conventional sensor, mode splitting is proportional 10 to minus 4. However, for this EP sensor, because splitting is proportional to scale as a square root of the perturbation, 10 to minus 4 become 10 to minus 2, 100 times enhancement, right? So we run experiments to show that yes, there is exception points enhancement when you use this new sensing mechanism. So about finishing up, 1 more minute, then I'm done, ready for question. So as I said, I found this Weisman-Geller structure can be used for many interesting applications. But how to push this beyond a lab and how to strengthen my collaboration with people outside my field? We do need a portable system, right? This is a conventional or standard setup we use in the lab. It's not feasible to take this to another lab, and it's definitely not cost effective. So for the past 2 years, we're trying to shrink everything to a portable system, and the project worked pretty well. It's also done by my graduate student, Xiang Yi. So he helped to design the circuits, and now we published a paper last year in Optics Press showing this phone-size Weisman-Geller microcavity sensing system. And this is just touch screen front panel, show the transmission spectrum. To make it more fun, my student also developed this iPhone app. For those of you who has iPhone, you can feel free to download this and stay tuned because we're trying to make it even more useful. There is an education. There is a simulator for education purpose, but I'm sorry, you cannot enjoy the full function of this because on the upper right panel, corner, there is a button shows connect. If you have hardware from my lab, then you can use this app to physically control our system. Here's a sample, show you how it works. So my students, this is my favorite park that is walking distance from my office. Here you can see the length scale showing how big the park is. My students mounted the Weisman-Geller structure sensor on the drone and fly over the park. And we did the first set of experiments, the thermal mapping. So these are the temperature measured by these commercial thermometers, and we also measured the resonance shift to map with the data collected by this commercial sensor. And data they match pretty well, so the results pretty encouraging. So we are pushing along that line of research. And however, in WashU, we don't have much experts about circuit design and the hardware design. If anyone here, professor or students, if you show interest in this kind of projects, I'll be more than happy to learn from you to make the system even better. Okay, time is up. I wanted to thank all the current members and former group members in my group that helped to make all the research feasible in my lab, and I also wanted to thank my collaborators and also my funding agency. Now I'm ready for questions.
Thank you very much for a wonderful presentation. We have a few minutes for questions, and we have another class. We're holding them outside while we have questions. So, questions, please.
A simple question. I didn't understand what was causing the degeneracy for the right going and the left going paths. Did you explain that and I missed it, or?
Degeneracy?
Yeah,
So,
I mean the frequency shifts. Why is there a why is the mode direction dependent?
Okay, so initially, if there is a clean resonator, right, it doesn't matter whether clockwise and counterclockwise, they are identical, right? However, if there is a nanoparticle, then actually there are two standing wave that be formed. One mode will have maximize the overlap with the particle. Another mode will try to avoid the overlap with the particle. So naturally, there exist two different modes because the particle they destroy the symmetry of the structure. So two modes are formed. So you can see the most bleeding. But if it's a clean resonator, it doesn't matter clockwise, counterclockwise, it's identical. That's why it's degenerate.
Other questions? So I have a question. So to achieve the exception points, is it important for the particles to be located at specific locations or just specific distances from
That's
each
a very
other?
good question. Actually, there's no particular position to put these two nanoscatter. If you move the second, it's about the relative position of the two scatter. If you move the second nanoparticle along the periphery of the ring, you can find a multiple location at which the system can operate around the exception points.
Other questions? Yes. Oh.
I can just speak up.
Sure.
All right. So, on what basis is the chirality of the mode selected in that experiment that you showed us, where unidirectional lasing was occurring?
Chirality.
Yeah. So, I mean, how is the chirality selected? Like, which chiral mode will be excited?
Oh, that's a very good question. So it's more like exception points, right? Exception points allow only one state because all the states collapse at one state. And then, for example, if initially there are two states that can exist, then it really depends on which exception points you choose. It can choose this or the other one. It doesn't matter. It really depends on which exception point you choose for the system.
So once an exceptional point is selected, then you just have one mode.
Exactly, either clockwise or counterclockwise. You can do a systematic investigation to show, okay, at this particular exception point it's clockwise. The other one is counterclockwise.
So does that mean that if you did a passive experiment without laser medium inside the cavity, would you see the mode one way in the waveguide but not the other way?
Yeah, for passive one,
Yeah.
for passive one, you see both. Then you see transmission both because it's biased, right? They're always transmission in the forward direction. So that's why we need to run these lasing experiments. Yeah, that's a very good question.
So any other questions, perhaps from a student? I'm challenging you today. Okay, well, let's thank our speaker again. Thank you so much.
Thank you.